Okay, this is a quick video about how batteries are organized in electric cars. So I'm going to show an example here of something that looks like a Tesla battery pack that you might find in a Model X or a Model S. So inside of these types of Tesla batteries, we have 6 groups of 76 cells in each group. Now each group is organized of 76 cells, all connected in parallel, so all the positives are connected to each other and all the negatives are connected to each other in each one of these groups of 76. Because they're connected in parallel, the voltage is still 3.75 volts. All we're doing is increasing the energy density, not the voltage. But having 6 groups like this is not much help. We need to join these up somehow. So you'll see this in the next slide. Imagine each of these green batteries here is a group of 76 cells, all held in parallel. We connect them together by connecting the positive of one group to the negative of the next, positive of the next group connected to the negative of the next. This is called series connection. So because these groups are now connected in series, the voltage multiplies up by the voltage of each individual group of 76 cells. So each one was 3.7 volts. We now have 6 groups in series, and now we get an output of 22 volts. And this varies somewhere between 20 and 25 volts depending on the state of charge. So a Tesla battery pack is often known as a 76P6S, so that's 76 parallel batteries in 6 groups in series. So if we have 6 groups of 76 cells, that's 456 cells in total. And each cell is called an 18650. It's made of lithium ion. And it's about the size of an AA battery, each one of those. So one 18650 battery has a capacity of 3500 milliampere hours, or we can convert that into watt hours by multiplying it by the voltage. So 3.7 volts times 3500 milliampere hours gives us one of these 18650 batteries can hold 13 watt hours of energy. If we have 456 of those at 13 watt hours, that gives us total amount of energy inside a Tesla battery pack of getting on for 6 kilowatt hours. Now, a smaller house might consume about 6 kilowatt hours of battery a day. A larger house maybe double that. So you can see how much energy is stored inside one of these Tesla battery packs. So we'll have a quick look at the battery pack, and then we'll have a look at something called a battery management system, which we use to manage the charging and discharging of one of these battery packs. Okay, so this is a Tesla battery pack, and you can see the individual 18650 cells inside here. These little rounds are the individual cells, each one the size of an AA battery. And this is the output terminal, this is the negative, and this is the positive. So if you measure the voltage between positive and the negative, we should see something around 20 to 25 volts. And these are the two connections where we get the power from to drive the motor in an electric vehicle, and it's also where we put the power in to recharge the battery. And these little wires you can see on here, they're used to measure the voltage across each of those 6 groups of 76 cells. And then we use this board here to connect onto each of those groups, and then we can monitor the voltage and manage how it gets charged up. So what we've got here is a little mock-up of what the Tesla battery looks like. Now we've got 6 cells in series, so the positive connects to the negative of each of those individual cells. I actually got these cells from used vapes, so I went to the supermarket and grabbed some used vapes put in for recycling, and inside of them are perfectly usable lithium ion batteries that can be recharged, and sadly these things often just get thrown away, but we can use them for something useful like this. So this is a little demonstration of something I'm using just to check the technology that will manage the battery packs in the EV conversion. Now if we look here, we've got these little boards here. Now each one of these boards is monitoring and managing each one of these cells. And so in the Tesla pack, each one of these boards can manage and monitor a group of 76 cells in parallel. So this is part of a system called DIY BMS, so it's not made by me. Well, I got these boards manufactured and then I soldered the components on there, but it's following instructions and designs from somebody online. I'll leave a link in the description. It's a pretty good system. It's called DIY BMS. So we've got 6 boards in here, each one monitoring one of the 6 cells here. And you can see the blue lights flashing across them. So there's a communication being sent between each of these boards, and each board is reporting 2 things. Number one, the voltage it sees across the battery. And the second thing it's reporting is the temperature of this board inside here. Now when this board is performing another of its functions, which is managing the charging process, you'll see that it needs to monitor the temperature of some resistors on here that help to discharge one of the cells that's getting a little bit too high compared to the others. Because the ideal situation when you're charging up cells is that they should all arrive at the maximum voltage at the same time, but because of differences in the chemistry and manufacturing processes, they don't always behave the same. So you've got to have some way of just taming one of the cells or 2 of the cells if they've reached their maximum, and allow the other cells in the group to come up to the maximum voltage all at the same time. I also have a little way of discharging these cells. So this is from the output, and these are 2 car light bulbs, so headlight bulbs, and I can plug this into here and you'll see that's pretty bright. So that's drawing what, 35 watts, so it's about 3 amps, something like that. Yeah, that's pretty bright. And what we can also do, if I connect up a charger, and now I'm starting to charge up these cells, and I'll show you what this board does. This board contains a little web server and allows us to see the voltages that are being sent out by these boards. So we'll have a look at that now. So this web page has been created by that small little board that sits to the side, and it's receiving information from each of the 6 boards that connected to each of the 6 cells. And we can see the voltage on each of those cells. Now, where this is configured is the maximum voltage we want for any one cell is 4.2 volts. And the maximum we want for the whole pack is around about 25.2. So if we consider each of those cells is 4.2, we multiply that by 6, that's about, yes, 25.2. So the maximum we want the whole pack to ever get to is 25.2 volts. But if we look at the voltages on here, we've got 4.18, 4.16, 4.15, 4.15, 4.15 and 4.183. So clearly the 4.183, 4.184 is a little bit higher than all of the other cells. And this one will reach 4.2 volts first. But we don't want the other batteries or the other cells to stop charging at that point because they're not full. So we have to have a way of controlling the voltage that, or the amount of charge that goes into this cell, so that it allows the other ones to catch up. So what we'll see when this reaches 4.2, this column will go red, and what the board that manages that cell is doing is it's connecting a resistor across the cell, which helps to take some of the power away from it, and so it doesn't charge as quickly. In fact, what will happen is the voltage will drop a little bit, and then it might need to just charge again. But with a bit of luck, when this hits 4.2 volts, we should see it start to manage the voltage. Now this one's hit 4.2 volts. We don't want this cell to go any higher than that. So now you can see it's turned red. What that's done now is it's connected a small resistor across that cell, and it will stop it from charging up anymore. In fact, now you see it's dropped back down again to 4.181 volts. And so it'll start trying to discharge this cell now, because it's done its job and it's just pushed it back a bit down below 4.2 volts. Now again, it'll charge up a bit more and it might get to 4.2 volts again, in which case we'll short circuit the cell and start to reduce how much charge it receives. But of course, by shorting a resistor across that cell, it generates a lot of heat, so we need to manage the temperatures, which you can see down at the bottom here. Right, so we're at a situation now where all of the cells have reached 4.2 or thereabouts, and they're all trying to discharge themselves because they're just touching onto 4.2 volts. We can see that the total voltage is 25.2, so normally the battery management system, it would say, right, stop charging because that battery is now completely full. And the best we'll ever achieve now is just shorting out across each of the cells as they hit 4.2, taking the voltage down a little bit and then having to charge back up to the maximum again. So at this point here, it's completely charged and we can stop.